Thank you very much for the kind introduction. I like computing, and today I want to talk about one family of computing devices I've grown dear to in basically the last year, and just tell you what experience I and others had with them, since they are kind of obscure. So, before explaining what a vector computer is, how about we just narrow down what a computer is for the sake of this discussion, or this presentation. A computer has functional units. Functional units get words from registers, and on these words they perform some often mathematical operation and write back a new word to the registers. Registers are in constant exchange with the memory, where things get loaded into registers or stored back into RAM, and all this is controlled by an instruction decoder and all kind of other stuff which is not that important today. So that is that's what I mean with a computer in this presentation. So that raises the question, what is an instruction? An instruction asks who gets processed, using what operation does the information get processed, and where to does it get stored, where does it end up. So what are words for computers? For visualization's sake, I decided a cube is 46-bit for this, because, well, we have, if we imagine that every single cube in there, in this 4x4 cube, could be on or off, we end up with 46 different bit states, which could be things, which is the same as a 46-bit word, and a 32-bit word would be the half of that, one dimension halved. And a word itself is not enough to draw meaning from. We also need a data type to describe how to interpret the word, because the same bit pattern can mean different things in different data types. So what is a vector computer? This kind of is the idea of a vector computer. A palette, collecting stuff in a central place and being able to transport it. So rewriting the same graph with that metaphor. A vector computer is not about carrying every single box, every single word to the functional units that get processed. No, we batch them up in one vector, putting them on a pallet, and then a forklift comes and carries them to the functional unit where they get processed, and then often a forklift waits at the other end, gets the result, and puts it back into vector registers. So why care about vector computing? Well, from an application point kind of view, there is scalar code and there is parallel code. Sometimes they're so tightly integrated that you can't easily ship off the parallel code to the GPU or something, because the latency and overhead would not make worth it. So a tight integration can be beneficial. Also, we might be experiencing a resurgence of vector computing through WISC-V. The WISC-V has this WISC-V vector extension, which is slowly finalizing and getting chips made for it, but with a pre-release version of it, 0.7.1, there is already hardware out there which implements this sadly outdated and in principle forever obscure subvariant of WISC-V, which is incompatible with the main thing. One example of such a board is the Milky Way Duo, which is a dual-core WISC-V processor, which has a small vector unit satisfying the spec mentioned on the slide. So I'm not here to talk about that tiny vector computer. I'm talking about my vector supercomputer, which in this case is two NEC Vector Engines 10C. This is the most bottom-of-the-barrel model. This is a workstation model with blower fan, not water-cooled or something fancy, and as such, I have two of them connected over PCIe to an AMD Threadripper 1950X, because I needed the PCIe lanes. And yeah, I will get to that. It will not be funny. And just because something fits doesn't mean you should plug into it. So if you happen to end up with a NEC Vector Engine, be aware that even though your PCIe 8-pin from the GPU fits inside that port, it doesn't belong there. it fits, but it shouldn't. Like with consumer electronics, you should expect, or like with electronics in general, if there is like some plug and some cable and they shouldn't go together, then they shouldn't fit together. But in this case, for whatever oversight, the NEC Vector Engine uses an EPS 12-volt connector, as it is more commonly known as the 8-pin CPU connector, and like has the same rating. Should you not have a spare 8-pin CPU connector from your power supply, NVIDIA has the same problem with the same circumstance with their workstation cards, where, for example, the A4000 also has the same connector, and there is an connector made for such NVIDIA cards where you can put in 2 8-pin PCIe cards, which then together are available as one EPS 12-volt and supplies sufficient voltage to the 300 watt, which can be drawn via the EPS 12-volt connector. So we talked about pallets as like things which we use to transport things, and if we like compare what is a vector computer, what does it mean to build something as a vector computer, then we should like also consider the size. If you recently upgraded your desktop CPU, you might have done the switch from AVX 256 to AVX 512. So you now have 512-bit wide vectors, which is completely and utterly dwarfed by a single vector from the NEC Vector Engine, which is 16,348 bits wide. It might be more convenient to think of it as 256 46-bit words. As for not only are the registers on the Vector Engine bigger, it's also twice as many of them. So it's a very different design, but that's what I'm here for and to tell you about. So how does it work internally? Are there like 256 arithmetic logic units in parallel? No, not quite. They internally work on groups of 32 46-bit words. And there are 5 functional units. 3 are for floating point numbers. The first 2 mostly do like fuse, multiply, add, and that kind of operations which occur in linear algebra, while the third FPU is fancy, I will call it, and has in-hardware instructions for square roots and division and other fun stuff like that, while ALUs operate on integers and as logical operations on the bits which make up those integers, like knotting a number. This happens on the ALU. Now, the NEC Vector Engine, with like its reordering capability and depipelining capability, can sustain all those units, keep them fed, and get results back. This, in the end, it has to be backed, of course, with 16,348-bit registers, so 1 mbit of registers alone per core. But a vector computer is not just vector units. There's also always a scalar part with it. And, well, this has its own sets of caches, and in the end, before the data goes out through the HBM, there's a last level cache which is shared and thus also provides synchronization between those 2. So I want to start with a simple instruction, which nowadays is pretty common and not spectacular, but has sparked wild conspiracy theories in the past as NSA instruction when they suddenly appeared in AMD CPUs without much fanfare. The idea is you have some number and you just count how many ones are in there. This is useful for various cryptographic applications, and I want to show you some snippets from the NEC ISA guide, so you can get a grasp how it looks. And in this case, we have 2 scalar registers, and the result of SX will be the population count of SY. The link down below was a link to a longer discussion of the NSA thing. But that's not enough. The NEC Vector Engine has also support for a really uncommon type to see in hardware, namely quadruple precision arithmetic. So floating point numbers which are 128 bits wide. That's only in the scalar part, not in the vector part. And it works by basically stringing two 46-bit registers together. And then just you can add, multiply, subtract, no division. But it shows like this is a kind of hardware operation you usually don't have for this data type. Then like vector predication, but to introduce that, I first want to do like introduce a basic vector operation. So far we only had scalar ones. If we look at the functional description below, we see a for loop which iterates between 0 and VL minus 1. What is VL? With a vector computer, you don't always have to use the entire vector length. You can say, well, I only want to iterate over 180 things, and then it will smartly discard the rest and like do things in hardware to make to not waste as much resources. And this way, it is really convenient if you have a for loop and there's just some remainder remaining. Well, you just do one iteration with that, and you don't have to like have special tails which unroll in different ways. All these worries are gone. Then we also have a flag in this instruction. If CS is 1, then just a single scalar value will be used to like shift all values to the right. While if CS is 0, instead a different vector will be queried and every element will have its own shift. Why have both? Communicating one number is a lot cheaper than communicating 256 numbers. So I guess from that standpoint it makes sense, and the ISI is designed to let a knowledgeable programmer or a knowledgeable compiler exploit such information. And then the interesting part is this if with the vector mask. If the vector mask is not set, nothing happens, and if it's set, then Vx is changed. This comes from the idea that sometimes doing a bit of extra work is quicker than trying to eliminate all the extra work. For example, like if you were a bus driver, you wouldn't remove all the bus seats you wouldn't be using. You will just be keeping the bus seats in place and drive from A to B. And if people don't use it, there's no need to put them outside to save a few grams, because that will be more effort overall. A similar analogy applies here. So those vector masks don't just randomly emerge. You can create them by like comparisons, operations, that kind of stuff. But you can also do operations between vector masks. This, if you really want to be clever about it, might allow you to implement some state machine where you then can basically have 256 parallel instances which all run through the same state machine, which could be neat for various parsing or something like that application, in particular since the NEC Vector Engine has generally an enormous memory bandwidth. Then, does someone know this code? There's also a colorful language in there. This code comes from Quake 3, also it's attributed. The history of the idea is longer but not relevant. There is some evil floating point trickery in there I'm not going to explain, but how this is interesting is that the NEC Vector Engine has exactly this operation, not exactly this implementation, but exactly this operation in hardware. So it has an inverse square root in hardware. Why would one need that? Well, it's designed for scientific applications, and sometimes there you want to normalize some data set, or it's also useful for calculating like velocities in 3D space. And it has a square root operation. It has a division operation. Why also produce a 1 over square root? Well, we only have like one unit which can do division in square roots, and if we just produce 1 over square root, we can just use the normal multiply unit, and that way we save cycles on the fancy FPU unit. What is kind of unsatisfying about this documentation is the precision of this approximation is system dependent. So if the last vector engine dies, we will never know. I don't like that idea. I've try to make some progress towards documenting how it works. For the 32-bit case, that is easy because they were just, well, that fits in RAM basically. 2 to the 32 is not that much anymore. But for the 46-bit case, I will need to be a bit more clever. And we also see here with CX and CX2 that it's possible to operate on the lower half or the upper half as single precision or both at the same time or as one 64-bit. Then this is an instruction. When I saw it, my reaction was, what the fun is that? If someone has a suggestion, you're welcome, but also the description doesn't yield anything, and the person who has the most convincing idea after the questions and talks to me will get a Milky V Duo small vector computer I talked about. But I'm kind of puzzled by this one. So, a short summary. It can execute scalar and vector code, and if you know that the scalar and vector instructions load and store from different addresses, you can also say that the vector unit can, on certain operations, ignore potential dependencies to unlock more performance. It's primarily made for scientific computation and has a powerful and orthogonal ISA with very wide vectors. Orthogonal in this context means there's a clear separation of concerns. You can, just looking at it, get a pretty good feeling what the instruction does. There is no complicated decoding which needs to be undone, which is kind of nice. And I have a bit more. It also has powerful ALUs, which can do everything a desktop LU you could wish for from, except it can do it with a lot of stuff at the same time. It also has a powerful FPU. What is not supported are shuffle operations, except in the case where you want to swap around 32 sized groups, because that's also what is used internally, and just the reordering logic is exposed to the user here. For the 10 and 20 generation, there is no support for 16-bit reduced precision numbers as are typical machine learning. With the third generation, this was introduced. And if someone asks for pricing, I think I got them quite for a steal. I noticed that they were, in my opinion, sold way undervalued somewhere in China, and I had a Chinese childhood friend I asked to, get them for me, and using, for 48 gigabytes of HBM in total, I think alone that price will be worth more than that. Then it's also recently turned out that the huge memory bandwidth those vector engines have is also really suited for certain machine learning application, in particular inference. If we look at this board snapshot, we see 6 tiles around the main tile. These are HBM stacks, which is high bandwidth memory, and normally you only get 4 with something usually. So this later was also someone tried around with it, and the story behind this is actually interesting. This was kind of motivated by the live stream where someone thought, Express AI, this person thought he owns vector engines himself. I later joined the live stream. Trying large language models on a vector engine would be fun, and then there was some collaboration, trying out some ideas, and it turns out Llama 2.c is just a plain C implementation of large language model just to understand it. And it didn't run perfectly right away, but when we removed the queue sort, because we don't want everything sorted, we just want the top k entries, and we switched the memory orders of the matrices from column major to row major, and then suddenly the NEC Vector Engine, which is newer than mine, handily beats an A100 in that particular workload. So talking about the software which comes with it and where it's stored, on the NEC Vector Engine itself, there is, as with any modern electronic product, firmware. There's an ARM core on it, which does power management, fan control, helps with device initiation. The kernel driver is open source, and I've successfully built it for a different Linux version than the vendor officially provides for Red Hat, but I've not try to build it for a different non-Red Hat derived thing. There's a closed source binary in userland which manage things from the host. There are compilers, and there are like typical scientific libraries like BLAST, the fastest Fourier transform in the West, Fourier-Laplace, stencil codes, and MPI. MPI is fun. Just some other binaries which are shipped with it. That's kind of fun stuff. Just some thing. So about the compilers, there is a proprietary compiler by NEC which supports x86-46 and the vector engine as a target. It can't be open source, I asked. Then there are two LLVM-derived compilers which are distributed, which are both based on horribly out-of-date LLVM versions. The reasons for that are kind of on the slide. Upstream LLVM supports the NEC Vector Engine, but it's not a build target by default. You can omit all the vector instructions if you want, but the vectorizers in those compilers aren't quite strong enough to make good use of those heavy vector units. Then, I promised homebrew. Here is 2048 on a NEC Vector Engine. I just took a single C file 2048 implementation. I ran that through the NEC compiler. I used ftrace, which will become relevant later. Then I ran the program. I played a bit. I got a score, not a good one. Actually, I just wanted a screenshot. And ftrace is where it gets interesting, because ftrace is a tool which reads out performance counters and makes them available to us. And using that, we can use that as guidance to what functions are potentially holding us back in terms of performance. In this case, often interesting columns are the VOP ratio and the average vector length. In the main function, we have an average vector length of 16. What does 16 have to do with 2048? Yeah, it's the board initialization. It detected that for loop, it vectorized that for loop. It didn't find anything else to vectorize, so it ended up with an average length of 16. And in a draw board, it found something else small to vectorize, but for example, the pushing blocks around based on pressing a key, it couldn't vectorize that. And this is an application you wouldn't want to run on the vector engine because it doesn't make good use of its resources, and then it's just like a slow scalar CPU. Now, soon audience participation. HTOP is a command line task manager on Linux. So if you compile HTOP and its dependencies, such as ncurses and so on, with the vector engine as a target and run it, what do you think will happen? Raise your hand if you think A, it won't compile or run. Okay. B, it runs on the vector host and shows vector engine processes. C, it runs on the vector engine and shows vector engine processes. D, it runs on the vector engine and shows vector host processes. Okay. And I didn't understand the question, but want to raise my arm anyway. You're welcome. Thank you for your participation. It's D. So what happens here? The vector engine, like the information HTOP gains about the system, often is not like through system calls directly, but instead by accessing the file system. Those file paths are kept from the x86 version, so it looks in the same places where it would find the x86 system information. A few data things are obviously corrupted. I don't think like this with the terabytes of virtual memory makes that much sense, and mem being over 100%, there's like something odd going on there, but overall I can show that it runs on the vector engine, but it displays data from the host in this kind of corrupted way. So is it a surprise you take some Linux, C, C++, Fortran app, compile it from source, and it runs, and then you just tweak the slowest part and it works, and then suddenly you have high performance? Well, there's some difference, and they are elaborated somewhere else, and the support for other programming languages is thin. Oh, then VIOS is what fakes Linux userland towards the processes running on the vector engine, and certain system calls like malloc are handled directly on the VE, while all others are passed through the vector host. it's best to think of the vector engine as a coprocessor because it doesn't have its own timing source. What actually happens to switch processes is that the vector host, the Intel or AMD CPU, holds the PCIe device, swaps out the content of the processor state over PCIe and kicks it again. Because it's kind of an expensive operation, the scheduling interval was decided to be a second. So it's also kind of funky watching how processors behave on there because they always stick for a second. Then we had like a situation where we have a binary running just on the vector engine, like with 2048 on top. There's also a possibility to take CUDA-like codes and use a replacement called Vader and have the main CPU offload some tasks to the vector engine, but this is the first time I've seen this in architecture. You can actually do the opposite. You can have an application running on the vector engine, which then hands off certain scalar-intensive workloads to the CPU and say, you deal with that. I keep crunching my big numbers, but I'm in charge. And that's like, kind of blew my mind. Then it was not everything rosy. I had problems getting it started. And so I decided to dig in the binary a bit. Like I didn't find anything with 16. I had problems with PCIe. I thought like maybe it was a 16 versus 8 lane problem. It was a problem, but I didn't find anything in the binary. So I looked like for version 3 and version 2. Maybe I found something else. When I looked for 2, I found something else. I found this snippet, which I kind of lightly annotated. And if we change the how deep to search determines how many options we see when we interact with the command line, and by just changing that 1 to a 2, we suddenly, left hand was before, right hand, we unlock interesting new operations, like flash read, write, dump, but a lot of interesting I/O. But, well, the most interesting thing is the signature, because we can now decrypt and re-encrypt the scripts the proprietary binary was executing. So it turns out instead of 8, there were 10 cores on a vector engine, and it might be able to enable more than one of them or tweak with the HBM megahertz rate. So yeah, vector engine has a bunch of properties you would want from an HPC cluster. I think, okay, let me just go quickly through that. You can split a single vector engine in 2 separate ones by separating the central brainstem, basically, and eliminating some newer problems. It's connected by internally fast network, which will be over PCIe. The file system is shared, as in it's shared with the host, because everything happens through the host. Users have no access to the compute resources themselves. This is also true with the vector engine, because you can't SSH into the vector engine. You can only SSH into its CPU, into a vector host which has the vector engine. Execution via job scheduling is possible. Slurm supports the vector engine kind of. And like vectorization and multi-node parallelism also unlocks a lot of performance with the NEC Vector Engine. So it can be like a little toy box of all the problems and all the fun you can have with HPC in one form factor, drawing less than 250 watts if really pushed. So there are multiple users, but I actually forgot to put one down. The one closest by is the Klimarechenzentrum, a climate research science thing, just a few hundred meters, I think, in that direction. I'm not sure. And they also have NEC Vector Engine. So that are the things I know, and not only those prestigious institutions, but also me. If you send me your preferred username and public key, I can give you access to my vector engines. You can play around with it. And yeah, I'm open to take questions.
So, if you have questions, please go to the microphones in the middle of the room. There are 4. Signal Angel, do we have questions from the internet?
Yes, we have one question. That is, how did you get your hands on this card?
Well, I first heard of it through like JuliaCon, where someone from NEC basically told us the hardware exists, and someone tried to like make Julia work on it a little. And then I just noticed that in my feed, some Japanese people I followed suddenly started posting about NEC Vector Engines being available on the used market, and then I asked where, and then I learned, well, in China, and I happened to have a Chinese friend, and well, then he bought them for me. I sent him German Christmas food as a thing in return for the effort, and we kind of had a deal with that, and I had the first one last year around this time, and the second one arrived recently, so I hadn't had much time to do firmware experimentation because I couldn't bear the thought of having no vector engines to have access to, but now that I have two, there are a bunch more options.
Okay, then microphone 1.
Yeah. So thank you first of all for the great presentation. So I want to ask you about this example that you showed about htop.c, right? So by default, what I understood that GCC does not support it. You have a proprietary compiler, right?
And LLVM-based compilers, and there is some work towards GCC, but it seems pretty abandoned. It looks like NEC decided to switch to LLVM at some point, but there is some repo, and I'm not sure what state it is in.
Okay. So if this or something like this, probably RISC-V, right, comes up with this kind of a vector engine, the entire user land needs to be compiled to take to use this acceleration, like what happens on the GPU. There's a CUDA driver that is involved, right? It has an NVCC compiler, and it sends everything to the accelerator GPU to get things accelerated.
Not
right?
only, that's one option. The other option is that you can just take an application and just execute it as an application on the NEC Vector Engine, and the complete control flow is on the NEC Vector Engine.
Okay.
Yeah.
Yeah, but then the entire user land has to be compiled
Please,
for
no
that guy.
discussions.
Is that correct? Is that understood?
It's a different instruction set architecture, of course.
Okay, thank you.
So, microphone 3.
The confusion vector instruction you mentioned, I think it's for FFTs where you basically have the elements of a complex number interleaved, so that you have a vector of complex numbers with both the real and the imaginary part interleaved in the same vector register, and you want to do basically the butterfly operation, and you do the same operation just with different signs on pairs of elements. That's why you have that instruction.
Do you also have a question?
You just wanted to know where it does that. And the question would be, how portable to different Linux distributions are the host tools? Are you required to run CentOS or Red Hat?
I have not experimented with anything else. I heard people trying it with Debian, but I'm not sure whether they gave up because of struggle or just because of lack of motivation and interest. I haven't heard that it's hard, but I haven't heard that it's easy either.
Signal Angel, do you have more questions?
So far, I don't see any more questions.
Then, microphone 1.
Hi. Thank you for your talk. I love these cards. We played around with them about 5 years ago. We had a nice HPC class where we compared the upcoming Intel many-core offerings with NEC's vector offering, and we basically found that the many-core systems, they're shit, and the NEC systems are the shit. So that was pretty fun. One thing we had back then they only had the NCC compiler, and it was kind of meh. So what's your experience with these 3 compilers? Do you have any results on how well the other ones perform in comparison?
I heard that the RVV was really advanced for its time, the region vectorizer one. I have not read enough into it to be qualified enough to make a statement, but definitely worth a try, and the NEC vectorizer is also okay.
Yeah, and so about your instruction, it looks a bit like a Horner scheme, yeah?
I think I want to take another question. We can chat later, of course.
Yeah, I wanted to give my guess for your instruction. But
okay. Then, okay, I take guesses later. We just do questions.
Hello? Yeah. Please, no discussions at the microphone. We have some more cues. Please make your questions short and precisely. Microphone 3, please.
Yeah, thanks for your talk. I enjoyed it, and I would like to ask, you mentioned that the NECs also had some kind of rather deep pipeline, and I'm not sure how exactly it works, but could you elaborate a little bit how it compares to a modern x86 pipeline? So is there a proper kind of branch prediction that usually GPUs don't have?
Not only branch prediction, but as far as I know, also mild to aggressive speculation about when vectors are finished, and then invalidation of results. So the job of the scalar unit is basically to keep the scalar code out of the way so the vector unit can run, and for that also I'm not qualified enough to evaluate that, but yeah.
Thanks.
Microphone 1, please.
Could we go back to the very beginning with the vector word size?
Vector word size, of course.
Because you mentioned it's 16348, and it
do I have the last 2 digits switch up? I don't think so. It looks right.
It doesn't look like a precise 16K. Is it intentional, or it is shortened internally for some reason?
It should be 256 times 64. The rest you can math out yourself.
So yeah, so it probably should be 16384.
Thank you for your question. Yeah.
Okay, we have Signal Angel. There are no questions? More questions from the internet? Microsoft 3, please.
So you mentioned that the vector CPU is out of order capable.
To some degree, yes. I
do
think.
You know, basically, if you use predication, does it really basically take advantage of the out of order capability if you have a predicated scatter-gather instruction to really process and chain partial results as soon as they become available and process the elements inside a vector out of order, or is it in order per vector or something?
I'm not sure with gather and get generally reduction operations. I don't know.
And I think, how high are the context switching costs if you want to switch between multiple vectorized applications? Do you have to basically dump the whole accelerator memory, or do you have any kind of ability to partition the card and quickly switch between?
There are 8 cores, or alternatively 2 times 4 cores, and those cores are cores, and if they want their context switched, the state of that particular core needs to be dumped to main memory of the CPU, and something else needs to be loaded in over PCIe.
Okay, final question, Microsoft 1.
Hey, great talk, man. My question is, how easy is it to program these devices? Like sometimes I see people, using manual assembly instructions for x86, and I'm wondering, do they have to get really low level programming these?
What I can say that people are able to take some code they kind of know, like someone once tried to run a Mandelbrot plotter. It took a few changes, like something about a while loop had to be changed, and then after some more changes it kind of vectorized decently. What I kind of like about the vector engine is that even there are no really obscure instructions you can't guess because the shuffle pattern is somehow strange. It really follows the idea that each piece of data stays in its lane, and the only thing where this breaks is this: you can shuffle 32 46-bit word blocks, but other than that, it's really straightforward to predict what it does.
Cool.
And
Thanks.
to search it for functionality you might want. Yeah.
Thanks.
Okay, then please applaud this great speaker, Johann-Tobias.